All right, folks, lecture number 30. Can people in the back hear okay? Excellent. Announcements. Composition corrections are due today. If you've been putting them off, you can put them off no longer. Please make changes to your old projects based on the feedback you received, and then run Python 3 OK -- submit to submit again. And then you will earn back points that you lost on compositions for projects 1, 2, and 3. Any questions about that? Okay. Homework 8 is due on Wednesday. There is a homework/project party tomorrow at the usual time, 5 p.m. in 2050 VLSB. And project 4, the big one, is due next week. Did I mention that it is big? So, there's the project homework party. If you want some help, go. If you haven't started, then you can't really get help. So make sure you get started. To encourage you to start early, we're adding 2 early submission bonus points to this project. 1 you get if you've completed questions 1 through 12 by this Friday. So get started early. And then you get the other one if you submit a day early. In order to earn these points, you have to run Python 3 OK -- submit and make sure that you've set up your group with your partner online so we know who's submitting with whom. So find your partner now, get started, and submit early. Questions about that? In order to get the early submission point, you have to pass all of the tests that we gave you for questions 1 through 12. So in addition to the project, which is required, there's also this optional recursive art contest. I encourage you all to apply. You just draw something cool, run it on your own interpreter, and show us the results. We'll put all the results in a gallery and let you vote on it. We've added some new graphics features over the weekend so that if you had an idea of something you wanted to draw, but you found it was hard to draw, you may now find that it's easier to draw because you can create custom colors and you can add pixels anywhere on the screen. So just as a demonstration of the kinds of things you can do with this, I'm going to show you how to draw a sphere. Now, I'm not going to go through all the math because you can read that online, but I just wanted to show you what it means to have these new features. So the new features let you do things like when you start up your scheme interpreter, you can draw an individual pixel, but individual pixels are really small, so I'm going to draw a big 20-sized pixel. So if I say pixel at position 1010, that's blue, it's going to draw a big blue square. So you can still use all the turtle graphics where you move forward and you turn right, but if you want to just put a dot in a particular place, now you have the means to do so. And if you want to put another dot next to it, you can do that as well. Fancy. You can also pick any color you want. Instead of just using named colors, you can build a color yourself by composing together red, green, and blue values. So you can make any color you want in this way. Like if I want to make chartreuse, then that's some red, a whole lot of green, and no blue. And let's put that at 1410. And now I have a beautiful chartreuse pixel. Don't ask me to spell chartreuse. It's very difficult. Okay, so what can you do with this? Well, I'll show you. I'm just going to reprise the content that happened in the extra bonus lecture last Thursday about how to draw spheres. I'm not going to give you the whole lecture. I'll just give you the 4-minute version so you know what it means to draw pixels and why you might want to do that. Okay, so there's this technique called ray tracing. This is not on an exam or anything like that. It's just extra bonus content because I think it's interesting anyway. It lets you draw a 3D scene on your 2D screen. So this is a 2-dimensional screen, but we want to be able to draw 3D objects. And the way you do it is that you imagine that every pixel on the screen has a line through it from your eye to the object that it strikes. So here's the scene we're going to build. See if I remember how to do this. Okay, so this is not what we're going to draw. This is the thing we're going to draw. We're going to draw an orb, a sphere centered at the origin, pretending that we're standing here where this blue dot is, and it's illuminated by a sun that's right here, or a light that's right here. Okay, so keep that structure in your mind. What we're drawing is this sphere, we're here, and the light that's illuminating it is there. Okay? That's what we want to be able to draw. So there's a sphere at the origin, there's the camera that's viewing the sphere, that's our perspective, and then there's the light that's illuminating the sphere. The way you draw the sphere, this is not to scale, but I'm just going to show you the geometry of the whole thing, and then we'll write the code. If this is the sphere, and this is the camera, and this is the light, what you want to figure out is what it looks like when you project this whole sphere onto something flat, like the screen. The way you project it onto something flat is that you imagine drawing a line through every pixel on the screen from the camera and figure out where it hits the sphere. We're going to draw a line up there, down there, down there, down there, down there, down there, and that will be everything. Okay, questions so far? Okay, how do I figure out the length of the line between my camera and where it intersects the sphere? Well, it turns out that you can do that by looking at every point along this line until you find one that's exactly the radius away from the origin. And the way you do that procedurally is that it's really quick to find the point along this line that's nearest to the origin. And then you can also do a little more computation to backtrack right back to the point where you intersect the sphere. If you want to know the algebra, it's on Wikipedia, or I can walk you through it in office hours or something like that, but I'm not going to make you all look at it right now. I'll just tell you in code how to do it in a second. But once you've found this point, the way you make it look like a sphere is you figure out whether or not this line hits the sphere or not by computing the distance to the sphere. And then you figure out how much light is shining on it. I promised a demo. Okay. So here's some scheme. Min and max are just basic things. You know about Cotter and Codditor. And then here's some functions that have to do with vectors. So if you've taken linear algebra, you might recognize what these mean. If not, just work with me here. But in this example, which I'll post online afterwards, you say where the camera is. Remember where that is? That's the blue dot looking down toward the sphere. I write down also where the light is. And then I say how much ambient light there is in the room. And then everything else I'm going to write for you. Okay, so for each point is a procedure that picks some size of the screen that we want to draw and calls some procedure for each point. Instead of you watching me type it in, I'll show you what it does. Okay, Python 3 scheme. We're going to load this example, and then I'll show you that if I say for each point up to size 5, some function like take all the xy pairs and print them out, close the print, close the lambda, close the for each point, then it's just going to say here's all the points. Okay, so this is useful because on my screen, I want to say, where are all the pixels? And for each pixel, I'm going to draw a line through it and see whether it hits the sphere or not. So let's do that. So to render it, I'm going to draw a black background. I'm going to have a big pixel size, so each dot will be 30 wide and 30 tall. I'll say the size of the thing I'm going to print out is just the minimum of the screen width and the screen height. So I'm going to draw a square that fills my whole screen. And then the last piece I'll have here is a procedure that centers stuff. So what does centering do? Well, okay, so if I set my pixel size to 30, then I can ask how many pixels can I fit on the screen? That's the screen width is 21. And centering just takes a number like 5 and subtracts 0.5 from it after dividing by 21. So 5 divided by 21 is some number. I just subtract that, and that gives me a number between negative 0.5 and 0.5. I think someone's distracted by a conversation over here. Can I help? It's coming from the sky? Please be quiet, Sky. Okay, so I have this whole box full of pixels that are numbered grids, and I'm actually fitting them. There's probably something important going on up there. If there's any like audio coming from the top, can you please turn it down? Thanks. Okay. And I'm trying to come up with numbers between negative 0.5 and 0.5 in both the horizontal and vertical direction. Okay, so then for each one, I'm going to decide what's the direction that I have to shoot my green line through, which I get just by listing the centered version of x, the centered version of y, and negative 1. Why negative 1? It's because in my graph, I want to go down this way, okay? So I want to go down toward the orb. That's the negative 1. And then for each direction, it's going to be like slightly offset from the axis here, so I can see all the different parts of the sphere. Now, in order to make sure that one direction isn't longer than another, I have to normalize. If you've taken linear algebra, maybe you know what that means. If not, just forget about it. Okay. So I've picked what direction I'm looking in, and the next thing I want to do is figure out how bright the sphere is in that direction. So that's the intensity that I get by tracing that line from the camera in that direction until I hit the sphere. Okay, so the last thing I'll do is I'll ask if it's the case that the intensity is greater than 0. If it is, then I'll draw a pixel. A pixel at xy, where I use the intensity to create a color. Close the pixel, close the if. Okay, so what is intensity? Well, I haven't actually written this code yet, so it's always going to return 1. So intensity will always return 1, and then I'll draw a pixel. And what does that pixel look like? Well, let's try it out. Python 3 scheme. Run my example. So what it's doing now is it's picking every pixel on this grid. It's deciding what color to draw it. And when it finishes all of that, it will have drawn a yellow square everywhere. Okay, so if you take 1, 1, 0, that's the color yellow. This does not look like a sphere yet, right? So it doesn't look like a sphere yet because we haven't actually implemented this procedure that computes the intensity of each pixel. Questions so far? Might be easier to ask questions when I get to the end of the demo, which will be in about 3 minutes. Okay. Okay, so what does it mean to trace in a direction? Well, I find the distance between the camera here and the sphere here, which means I'm going to find this whole line and then how much I backtrack. Like I mentioned, that involves quite a bit of algebra, but that first leg is the whole line to the nearest point, which you get by just taking the dot product between the camera and the direction, and then we'll negate that. Then we have to define the length of that purple bar up there. Now, to do this, you have to solve the quadratic formula. So this is a lot of algebra. I'm not going to tell you how to do it. I'm just going to write it down. and we can talk about it later if you want. But let's just call that how much you backtrack squared. Well, that is the leg squared minus the length from the origin to the camera minus the radius of the circle squared, which is 1. And then I ask if it's the case that BB is less than or equal to 0, then there is no distance. Otherwise, the distance is the leg minus the square root of BB. Okay, what's this if statement all about? Imagine if you drew a line through the very top of the screen, then it would go off into the distance and never hit the sphere. So that one doesn't count. But if you do hit the sphere, then that does count, and this magic number BB, which comes from algebra, there isn't a good explanation of it, will tell us whether that happens or not. Okay, so now if I run my example, we'll shoot beams through every point in the screen. If they hit the sphere, then we'll say it's intensity 1. Otherwise, we'll say it's intensity 0. So this is what a sphere looks like if you don't shade it in at all and you look at it straight on. So we're like looking at it straight on, right like that. Okay? But wouldn't it look cool if it was shaded in somehow? Well, the shading comes from computing the angle between the line that gets you to the point on the sphere that you intersected and the line that goes to the light. So if these are in totally different directions, then there's no light on the sphere. If they're perfectly lined up, then it's a bright point on the sphere. And if there's like a big angle in between them, then there's kind of a light. So that means we have to figure out where's the surface of the sphere that we've struck. And you can get that just by starting at the camera and then following the direction, the distance that we traveled in order to reach the sphere. Now we also need to know this second line, the one that goes from the surface to the light. And you get that just by, we'll call that the beam, by subtracting from the light the surface. Okay, finally, what we'd like to do is just return an intensity that measures the angle between these two things, which we get, again, if you know linear algebra, you might understand this, otherwise you won't. You get from a dot product between the normalized beam of light and the surface of the sphere. Okay, what's it look like now? Well, now it's going to draw all the lines. If it hits the sphere, then it will calculate just how bright it is. Does that look like a sphere? It's like a sphere if you had a light here, but everything else was deep blackness, which is not really how the world works. In the world, there's light bouncing around in all directions. So we can get some of that by adding ambient light, which up here you see is just 0.2. So I add ambient light to it, and I'm going to add together the ambient light times the direct light from our light source, which I'll say is 1 minus the ambient light times whatever I had before. Oh no, an error, because that's not how you subtract in Scheme. That's how you subtract in Scheme. Oh, look at that orb. That's better, right? So that's ugly because the pixels are so big. Maybe I could make the pixels smaller and then it would look cool. Now the only problem is if you make the pixels smaller, then you have to draw more pixels. So if you look at the code, you'll see now the size is really big because the screen width is bigger and the screen height is bigger, which means it just takes longer to draw this thing, which means I have to come up with something to say while it's shooting all these lines through every single pixel until it draws the sphere. Okay, hopefully that inspired you to dig deeper into the graphics contest. It is totally optional. You don't have to work on it if you don't want to. You don't have to use pixels. You can just draw a cool tree, anything you want. But I wanted to make sure everybody had a chance to work on this kind of thing if it was interesting to you. Someone's got to ask one question. Yeah. Oh, so how can you speed things up? Most of the speed here, the problem with the speed here is that we wrote our own interpreter, which runs on top of the Python interpreter. And so we're keeping track of our own stack and all that, and we might not be doing it that efficiently. So the way we'd increase render speed here is we'd check to make sure that we weren't doing any extra operations when we were looking inside an environment or something like that. And people have worked on making their interpreter implementation more efficient for this graphics contest before, and it's helped a lot. Yeah, so I just added the pixels over the weekend so that you could run this example without writing a whole bunch of tiny squares or whatever. Okay. Thanks for indulging me. Back to course content. Okay, so we've been talking about how to represent lots of data and how to have implicit representations of sequences. So we talked about iterators last time, where you figure out how to compute the next element of a sequence from the current element, but you don't necessarily build out the whole sequence. And streams are another way to do that. Streams are the implicit equivalent to linked lists, which we learned about earlier in the course. You say what the first element is, and then you describe how you would compute the rest of the linked list. Okay, we call these streams lazy linked lists because the rest of the list is not explicit. It's not actually stored in memory. Instead, it's only computed on demand. So if some other function asks, what's the fourth element in this list, the rest of the first element and the rest of the rest of the rest of the list, then we compute it. Otherwise, we don't. So a linked list is constructed from any first element you want, but the second element had to be a linked list instance or the special value link.empty. Streams are just like that. The first element can be anything, but the second element is weird. The second element is a function that computes the rest of the list. So it's a function that takes 0 arguments, and it has to return either a stream instance or an empty stream. Now, why is it a function? It's because we don't necessarily call it. We only call it if somebody asks for the rest of the stream. Okay, once you create a stream or a link, they can be used interchangeably. So all the examples that you're used to still work. You can look at the first element, you can look at the rest of the list or the rest of the stream. But they're different because the rest of the stream doesn't actually exist unless you ask for it. Okay, so the linked class, I think we already know how that works. I create a linked list by creating a linked list with the first element 1, and the rest of the list has element 2 in it. And then if I ask for the first thing, I get 1. And if I ask for the first thing in the rest of the list, I get 2. A stream I create with the element 1 followed by a function that returns a stream containing element 2. st.first is 1, st.rest.first is also 2. So I created 2 equivalent things. But one of them did all of its computation up front. That's how link works. And one of them delayed computation until I asked for it. That's how streams work. So what is ST? Well, it's a stream that starts with 1, and then it's got something after it. But unless we look it up, we don't know what it is. And what's the rest? Well, that starts with 2. Whereas S has 1 and 2 explicitly in it. Oh, interesting. Now let's see if we can find a difference. If I create a linked list with 1 followed by a link with 1 divided by 0, what's going to happen? Error. 0 division error. If I create a stream starting with 1 followed by a function that computes a stream starting with 1 divided by 0, what do I get? Oh, no error. A stream that starts with 1 followed by something. Let's give it a name. S dot first is 1. What's the rest of S? Oh, now I get an error. So if somebody actually asks for the rest of a stream, then it computes the rest of the stream. And if that makes an error, then we have an error. How are we doing? Still have weird voices from on high. Sorry about that. Okay. Why would I do this? Well, what if I wanted to create a linked list of all integers? Well, that sounds difficult. There's a lot of integers. Infinitely many. That's going to run out of memory in my machine. However, I can create a stream of all integers, which implicitly represents an infinitely long sequence of numbers. But I'll only compute the ones that anybody bothers to ask for. So an integer stream is a stream of all consecutive integers without any bound. It starts with the first, which is the first number is 1. And then I build a stream using the first number 1 and a function that computes the rest of the stream, starting at first plus 1, or 2. Here's the implementation. It says make an integer stream starting at the number first, which by default is 1. What I'm going to return is a stream starting with first, and then if anybody asks what the rest of the stream is, I'll compute the rest, which is an integer stream starting at first plus 1. Whoa. There's some recursion going on here, folks. Does this really work? Let's try it out. Okay, we'll put that over there. We'll start up that guy. 2, 3, 4, 5, 6, 7, 8. Make it big. Get rid of some junk we don't need. We're going to define int stream, which starts at some first value, the first integer. It returns a stream with first, and then some function for computing the rest. What was compute rest? Well, that was a 0-argument function that returned the int stream starting at first plus 1. If I create an int stream starting at 1, how does it behave? So S is a stream starting at 1. That's the first element. The rest of first is an error. Oh, because I can't type. Is 2. The rest of the rest, first element is 3. The rest of the rest of the rest of the rest, first element is 4. That's kind of a pain to type. So I wrote a convenience function called firstk, which takes in a stream and gives you the first and the rest first and the rest first, all the way up to k of them. So we can see what's in a stream. And I could have written it like this, too. I could have taken this int stream expression and put it in lambda. Oops. In lambda right there. That does the same thing. How about questions about that? So this is a stream defined, a function that returns a stream where the rest of the stream is defined in terms of the function that computes the stream. That's fundamentally how streams work, is that the rest is a function that computes the rest of the stream. Uh-huh. Yeah, you can kind of do whatever you want. So anything you can build into a linked list, you can build into a stream. How do you list the whole number line? Well, it is a sequence, so it has to start somewhere And so to get all the positives and all the negatives, you have to bounce around in some way. Mathematicians talk about how to bounce around a lot, I think. So a stream can represent an infinite amount of stuff. A range cannot. A stream can also contain kind of arbitrary stuff in it. It doesn't just have to contain consecutive integers. We could put consecutive squares or anything like that. So it's a much richer representation than a range. Good question. You want to try some? I'm going to give you 4 different functions, and I'm going to give you 4 different pairs of the first thing and the first thing in the rest, or the second thing. And you try to figure out which one matches up with which, while I try to make the voice from on high go away. Okay, do that. You can talk to the person next to you. Okay, how many people want more time? How many people don't want more time? More time it is. You got to vote to get what you want. Okay. So if I create a stream where x starts out as 1, and I put it in a list, then the first element will be a list containing 1. When I compute the rest of the stream, so I guess this wasn't clear, but I was assuming this f calls this f, and this f calls this f, etc. When I compute the rest of the stream, I'm going to pass in a list containing 1, which will be put in a list, so I'll get a list within a list containing 1 as the second element. And the third element will be a list within a list within a list containing 1. This says I start with a list containing 1, and that's the first element. The second element I get when I add 2 lists together. When I add 2 lists together, I'll get a 2-element list containing 1 and 1, which I'll then pass in as x. And so the third element will involve a list containing 1, 1, followed by 1, or 3 1s in a row. So it's that sequence. Okay, this one's weird. This says x is 1. I create a stream called S, which starts with a list S, followed by the stream called S. Okay, so if the rest of the stream is just S, then the first element in the rest of the stream is just the same thing, a list containing 1. And the last one, should we even do it, or do we know about process of elimination? Okay, we'll do it. Okay, so what this says is I created one list in the first place. I appended 1 to it, and I put that at the beginning of the stream. Then I called f on that very same list. When you have two different names for the same thing, appending to one changes the other because they're both the same thing, which means I'm actually changing the first element of the stream to add 1 to that as well. Yes, then it will mutate every element, and then we'll have them all. They're all just names for the same thing, and they'll get arbitrarily bigger. Oh, that's true. If I called s.first without ever calling res.first, then it would be this top answer here. So this would be a lousy exam question for that reason. Thank you very much. Okay, other questions? Over here? Yeah, in my mind, I was thinking you had just called s.first and s.res.first, and you wanted to look at the different values. Okay. Streams might not seem that special right now, because they're just like linked lists, except for maybe they're longer. But they do allow you to define them recursively in ways that are quite powerful. So let's look at some examples. Let's say I have a stream already, and I want to square everything in that stream. Well, then I can compute the first thing just by squaring the first element of S, and then I return a stream with that first element. I write a function that computes the rest of the stream, which is just the square of the rest of S. So S is the integer stream. Its first k are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I say SS is what I get by squaring S, then the first element of S is 1. The first element of of SS is 4. And if I get the first k of SS, I'll see 1, 4, 9, 16, all the way up to 100. Okay, what's going on here? Well, I defined how to square the first thing, but then I also applied that to the rest of the stream, which means the first thing is now the second thing, because the first of the rest of S is the second thing in S. So I've also defined how to square the second element, and the third, and the fourth. This is like a crazy example. I mean, once you get used to streams, this is totally ordinary. But the first time you see this, you should be thinking, how come we don't have to say, do it over and over and over again? Well, the way we're saying do it over and over and over again is to recursively define what a square stream is in terms of a square stream on the rest of the stream. Yeah, so lambda doesn't take any arguments. Whenever I write s.rest, what's happening is it's finding a function, this function, and calling it with no arguments. So if I said f is lambda 12, then f is some function, and I call it with no arguments like that. And that's what's happening kind of behind the scenes here. At the end of the lecture, I'll show you the implementation so you know exactly why it works this way. No, so s.rest does the calling already. So if you must know, buried within here is a function that computes the rest. And you could call that in order to get the 2. But we don't do that. Instead, we just say s.rest directly. Okay. Should we do some more recursive, crazy processing? Let's do it. Let's add two streams S and T together. What's the first element? If you add the first element of S with the first element of T, and then you want to add the second element of S with the second element of T, and then add the third with the third and the fourth with the fourth, and that's how you build a new stream. How do you get the first thing? S.first plus T.first. How do you get the rest? Well, you got the first, and then we need some way of computing the rest. Computing the rest is a function that takes no arguments, and it returns what you get when you add together S.rest and T.rest. Let's call this thing add stream instead so we don't get confused. Okay, so here's the stream of all ones. It's a stream that starts with 1. What's the rest of the stream of all ones? It's the stream of all ones. What's the first thing in ones? 1. What's the rest? 1. What are the first k element in ones? Just a bunch of ones. What about twos? I can get twos by adding together the stream of ones with the stream of ones. What are the first k elements of twos? Bunch of twos. That's kind of cool, but what's up? Oh, so twos.rest is a stream that starts with 2, and I haven't computed the rest yet. But if I did, I'd just find a stream full of twos. So instead of using compute rest, I could just add the streams. Is that what you're suggesting? That won't work because you have to have a function here. So that's how streams work, because the second element always has to be a function. Otherwise, we'll get an error. So I could make it a function by adding a lambda there, and then I'd have something equivalent. Oh, I lost my ones and my twos. Oh, I need a k. 10 twos. But if I didn't have this here, then it would say you tried to create a stream without using a function. So let's try it really quick. Get my ones back, and then I'll add them together, and it will just complain. Okay, so it tried to call addStream, which involved calling addStream, which involved calling addStream, and so we ran forever. So you really do need that lambda there. And if I just put like a number here, like stream of 1 and 2, then it would say compute rest, the second thing, needs to be a function. Question? True. Yeah. Oh. Do we even have twos right now? We don't. We've got to go back to a stable state. That looks pretty stable. Okay, so we got ones, we got twos. Twos.rest is twos.rest.rest. They're the same, what? Fascinating. Oh, let me correct myself. Ones.rest is ones.rest.rest. That's true, because we defined ones in terms of itself. Twos is a completely different beast. Twos is what you get from addStream, which creates a brand new stream each time. I'm glad I did the example so I could correct my error. Yeah. We've built this stream. I'll show you the implementation in about, actually, maybe I'll show you at the beginning of next lecture. So addStreams doesn't consume any more memory than what you ask for. That's kind of the magic of addStreams, is that it only computes the first element unless you ask for more. So addStreams doesn't use up all your memory instantaneously. It just adds the first thing, and then if you ask for it, it'll add the rest. How do I create this stream of all integers? Well, that's 1. And then if I want the rest of the integers is just one more than the integers. So 1 plus 1 is 2, and 1 plus 2 is 3, and 1 plus 3 is 4. So I could just add the following two streams together. I could add the ones and the ints. No add streams. Oh, boring. Ints.first is 1, ints.rest.first is 2, ints.rest.rest.first is... I can't type today, folks. Okay, so what's supposed to be on the screen is I create the int stream, and then I ask for the first part, and then I ask for the rest of the first, and then I ask for the first k of the ints, and I get all the first k. And the only streams I've used are ones, and then ints, which is defined in terms of itself. The rest of the stream of integers is just the stream of integers with 1 added to every element. That's some fancy math. Okay, you want to see the implementation, or you want to see more examples? Let's do more examples. I voted for you. Okay, one more example. Then at the beginning of next lecture, I'll walk through the implementation of how streams are written, or you can watch the video yourself, but I will go through it in lecture on Wednesday. Okay, so more examples. Let me show you functions that take functions and apply them to whole streams. So we talked about map 2 lectures ago. Mapping a function over a stream is like mapping a function over a list. It applies a function to every element, but it only does it on demand. So what it does in the implementation is it looks to see if the stream is empty. If so, there's nothing to map the function over. Otherwise, it applies the function to the first element and defines a function that will apply the function to the rest of the stream. Okay, so the point is when you call mapStream to double every element in the integers, it's only going to double the first thing right there, unless somebody asks for the next thing. Compute rest is not called unless somebody asks for the rest of the stream. So if I create an integer stream, which starts at 3, and then I map the function that squares, and I ask for the first 5, then it will have squared the first 5 elements, but it won't have taken infinitely long, because I only asked for the first 5 elements. I never asked for the 6th thing. So 8 never got squared. Sorry, this is a little bit funny. Okay, what about filtering a stream? So filtering a stream means you take a function, you take a stream, and you return a stream with all the elements for which the function is true. Filter stream takes a function and some stream. If the stream is empty, we're done filtering it. Otherwise, if it's true that applying the function to the first element of the stream, then I create a stream with that first element, and I compute the rest. Otherwise, I want to throw out the first element, which means computing the rest, which means filtering the rest of the stream. You got energy for one more cool example? It might take 2 minutes instead of 1. I'll do my best. Let's say you want a stream of all prime numbers. How would you get that? Well, the stream of integers not divisible by any k less than or equal to n is the stream of all primes. And it's the same as the stream of all integers not divisible by any k less than n, filtered to remove anything divisible by n. And this is called the sieve of Eratosthenes, who was not a computer scientist. Okay, here's a mathematician. So the idea here is if I take the whole number line, I can find the primes by looking at the first thing and filtering out all of its multiples. So 4, 6, 8, 10, and 12 are gone. Then I look at the next thing and I filter out all of its multiples. So 9 and 15 are gone. Then I look at the next thing and filter out all of its multiples. So 25 and 35 are gone. And I can write that in just a little bit of code. A lot of technical issues today. Okay, so how do I find all the primes, starting with all the integers? Well, what I do is define what it means to be not divisible by the first thing in S. So k is not divisible by the first thing in S if this does not equal 0. You're used to that. Now, what about computing the rest of this stream? Well, to do that, I'm going to need to return the result of calling primes on the filtered version of the stream, where we filter by not divisible on s.rest. Divisible. And I need to return. I love having on-the-fly debugging from the audience. Keep it up. Okay, so to finish, I need to create a stream that starts with s.first, and then I compute the rest. And when I do that, I create primes starting with an int stream, starting at the first prime number, which is 2. The next prime number is 3. The next prime number is 5. The first 100 prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, 23, blah, 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 all the way up to 541. Okay, I'll see you on Wednesday.